In this video, we are going to see some related rates problems. In the first question, we are given that a rectangular swimming pool, which is 10 feet wide by 20 feet long, of uniform depth, is being filled with water. T is a variable used to indicate elapsed time, H is the height of water, and V is the volume. The question is asking you to relate the volume to the height. Now, since this is a rectangular pool, the volume is given by length times width times height. The length and the width are fixed, right? So those are given by 20 times 10, so 200. H is the only variable in this situation. So then when you take the derivative, your dv dt, the derivative of v with respect to time is nothing but 200 times dh dt. Okay, so this is the relationship. The question is asking you at what rate is the volume of the water increasing if the water level is rising at the rate of 1/4 feet per minute. So the question is asking you what is dv dt when dh dt is 1/4. Okay, so when you do this, you reduce this. So this goes 2 times into, this goes 100, 50, right? So this is 50 cubic feet per minute is the rate at which the volume is increasing. Okay, next question. At what rate is the water level rising if the pool is filled at the rate of 10 cubic feet per minute? Okay. So now remember, we had this relationship between the rate of change of volume and the rate of change of height. So this is the relationship, right? Now in this instance, what is given is our dv dt is given to be 10, right? And then the question is asking you, what is dh dt? So you substitute this, your unknown is dh dt, you divide by 200 on both sides. So you get 1/20 feet per minute is the rate at which your height is changing. Okay. Next question. The area of a circle increases at the rate of 1 centimeter cube per second. How fast is the radius changing when the radius is 2 centimeters? So the question is asking you, how is dr dt if you use r to indicate radius? So what is this rate of change when r is equal to 2? This is the question. Now we all know that the area of a circle is given by pi r squared, right? So dA dt is 2 pi r dr dt, right? So then the question is asking you, if dA dt is 1 and r is 2, what is dr dt? So if you solve for this, your dr dt is going to be 1/4 pi centimeter per second. Okay. How fast is the circumference changing? Circumference is given by 2 pi r. So the rate of change of circumference is 2 pi dr dt. And the question is asking you at what rate is this changing when the radius is 2 centimeters. So here the dr dt from the previous problem was 1/4 pi, right? So you do this and you'll get 1/2 centimeter per second is the rate at which the circumference is changing. Okay. Okay. In this next problem, two boats leave a port at the same time. One travels west at the rate of 20 miles per hour, and the other is traveling south at the rate of 15 miles per hour. After 30 minutes, how far is each boat from the port? Now, let me call this boat A and this boat B. Okay. So, boat A is traveling at 20 miles per hour, right? Um, so 20 miles per hour. After half an hour is half an hour. So that means 10 miles, right? It has traveled 10 miles. What about B? B is 15 times 1/2. So that is 7.5 miles. So that is how far they are. Okay. Then, at what rate is the distance between the boats changing 30 minutes later? Now, let's connect these two. So, this is the distance between the two boats, correct? So, this is the distance between two boats, and let me represent that by the letter S, okay? So, then what I'm going to do is I'm going to represent this distance by X, this distance by Y. So now, as you can see, there is a right triangle formed, and the geometric equation that I can use to connect these three variables is x squared plus y squared is s squared. Okay. So then I take the derivative with respect to t. I get 2x dx dt plus 2y dy dt is 2s ds dt. So what we are doing here is we are doing the chain rule as well as implicit differentiation. Okay, so that's what we have done to get this. So now you already know that this represents x 30 minutes later. This represents y 30 minutes later. Dx dt is 20, dy dt is 15. So let us substitute all of that. So you know that 30 minutes later, this boat has traveled 10 miles. It is traveling at 20 miles per hour. This one has traveled 7.5. It is traveling at 15 miles per hour. Now we are asked to find ds dt, but you see that s is missing at that instant. So now what can I do? I can use the same relationship to find s at that instant. So what I'm going to do is I'm going to take this to the side. So I'm going to say 30 minutes later, right? What do I have in this triangle? I know that boat A has traveled 10 miles. Boat B has traveled 7.5 miles. So what is the distance between the two of them? So that is given by 10 squared plus 7.5 squared. So S is nothing but square root of 10 squared plus 7.5 squared. Okay. So this is what I have. So let me use Desmos to just get this pretty quickly. So I'm going to use my Desmos scientific calculator. I'm going to start this, and I'm going to have 10 squared plus 7.5 squared. So that is 12.5. Okay, so then I'm going to go back to this, and I'm going to put 12.5 in here. Okay, so then I'm going to simplify. 2 times 10 is 20 times 20 is 400. 15 times 15 is 225. 12.5 times 2 is 25. Combine 625 is 25 ds dt, which means ds dt is 625 over 25. Okay, so if you want, you can go back and use a calculator for this, even though you might not need that. So you have 625 divided by 25, which is 25. So I have 25 miles per hour is the rate at which the distance between the two boats is changing. Okay. Okay, makes sense? All right. Next one. An airliner passes over an airport at noon, traveling at 500. So this problem is similar to the previous problem, right? So this is traveling at 500 miles per hour west, and then another one passes the airport as the same elevation, traveling due north at 550 miles per hour. Assuming both maintain their elevations, how fast is the distance between them changing at 2:30 p.m.? Okay. Now, they are leaving at 1 p.m., correct? So we're going to use the same relationship. I'm going to call this X, I'm going to call this Y. So I'm just going to find out. So they are leaving at 1, and then we are the time that we are interested in is at 2:30. That means the airlines have, I mean, the planes have already flown for an hour and a half. So what will be X? So at 2:30 p.m., X will be what? X will be 500, right? 500 times 1.5, right? So that is what X is. So that is 750 miles. Y will be 550 times 1.5. So that is 550 plus 275, right? 825 miles. Okay. So that's what we have as the distance between them. Now at the same instant, I'm going to find what S is. So S will be square root of 750 squared plus 825 squared. So this is using the Pythagorean theorem that we used in the last problem. So I'm just going to do that and get the answer right away here. So I have square root of 750 squared plus 825 squared. So that is around 1115. Okay, 1115. So this is approximately 1115 miles. Okay. So then I go back here and do the same thing. S squared is x squared plus y squared. 2s ds dt is 2x dx dt plus 2y dy dt. So that is 2 times 1115 ds dt equals 2 times 750 times 500 plus 2 times 825 times 550. So then you'll just have to do the arithmetic here. Okay, so this is 1000, right? So 750 plus this one is okay, 2 825 550. 2 times 825 times 550. Okay, that is 907,500. 907,500. Okay, this is 2230 dsdt. So dsdt is this plus this over that. All over 1115. So that is 1487. So this is the rate at which the distance between the two airlines is changing. So these two problems that we just did uses the Pythagorean theorem and the right triangle for calculating the rate of change. Now in this next problem, we are going to look at a right circular cone, right? So there is an inverted conical water tank with a height of 12 feet and radius of 6 feet. Now these two measurements, the 12 feet height and the 6 feet radius, are never changing, right? So those dimensions remains intact. Now, what is happening is the water is leaking out of this at the rate of 2 cubic foot per second. So because water is leaking, we are given that dV dt is 2 cubic feet per second. And because water is leaking, I'm going to put a negative over here. Then, um, okay, so what is the rate of change of the water depth when the water depth is, so they're asking you what is dH dt when H is equal to 3? This is the question, okay? So this water level, because water is dripping, you're having this water level um, is changing, right? So the R of that water level and the H of the water level are constantly changing, but there is a relationship between R and H. So what we are going to do is we are going to first see that the rate given to us is the volume. The rate that they're asking for us is the height. So let us see what is the relationship between these two variables. So the relationship between these two variables is that volume is 1/3 pi r squared h. But as you can see, we have three variables, but we have only one rate given to us. So in these kinds of situations, we have to see whether we can rewrite so that there are only two variables involved. So for that, we are going to look at this cone and know that for the cone here, we are going to use the similar triangle concept. Okay, so how are we going to use that? This cone is 12 feet height and 6 feet radius is always fixed. And this is the R and the H of the water level. So which means R and H are changing at the rate of 6 over 12. Or rather, R is 1/2 H. So this is the relationship between R and H. Now, since I want H, I'm going to go ahead and rewrite R in terms of H like so. So I'm going to just replace R in terms of H. So then I replace and I get only one variable. 1/2 times 1/2 is 1/4. 1/4 times 1/3 is 1/12. I get pi h cubed. So this becomes the relationship between V and H. So now we have rewritten our equation in only two variables. So now we take the implicit differentiation and we get dV dt is 1/12 pi 3h squared dH dt. Now the instant that we are interested in is when the height is 3. So what we are going to do is we are going to replace 3 here. 3 squared is 9. 9 times 3 is 27. And dV dt is given to be -2. So then I solve. So I rearrange things. That this 2 goes there. So becomes -4 over 27 pi, right? And what is my unit here? My unit is feet per second. So this is the rate at which the height of the water level is decreasing. Okay. And that's all you have to do. So here we use the concept of similar triangles. Okay, now the same thing above, the question asks if the water level drops at, so now we are given dH dt to be -1 feet per minute. The question is asking you at what rate is the water draining from the tank. So now we have already established that dv dt is equal to 1/2, 3/2 pi 8 squared. So this is what we have. So all we need to do is substitute. But now the water depth is given to be 6 feet. So we substitute and this is what we have. So 6 squared is 36. 36 divided by 2 is 18. 18 times 3 is 54. And that is our answer. Okay. All right. So in this problem, we have two shapes involved. There is a cone and a cylinder. So what is happening is that water from the conical tank is draining into a cylindrical tank. Okay. So the water is dropping from the conical tank at the rate of 0.5 meters per minute. Wait. Oh, the water level is changing at the rate of 0.5 per minute. And what rate does the water level in the cylindrical tank raise if at 3 meters? In the conical tank is 3 meters. Okay, so because we have height and radius and everything involved, so we don't want to be confused here, right? So what I'm going to do is I'm going to declare this radius as R1, this height as H1. As far as the cylinder is concerned, the radius is not going to change, it's only the height. So I'm going to call this height H2, okay? So this relationship for the volume here is 1/3 pi R1 squared H1, okay? Water level is changing at zero point 0.5. Okay, so now what I'm going to do is I'm going to do the same thing that I did in the previous problem to find out the rate at which the volume is changing for the conical tank. Okay, so now again, I'm going to use the similar triangle concept and I'm going to say that if this is 4 and 5 and this is R and H, my R over H is 4 over 5, 4 over 5. So R is 4/5 H. This is the relationship between R and H for the conical tank. So which means that my dV, before I write dV dt, let me just write. So this is for the conical tank. I know that the volume is 1/3 pi R1 squared H1, right? So now I'm going to write this as 4/5 H1 squared H1. So then when I simplify this, 4 squared is 16, this is 25, H1 cubed. So then this can be written as 16 pi over 75 H1 cubed is the relationship between volume and height for the conical tank. Now I take this, I differentiate this and I have dV dt is 16 pi over 75, 3h1 squared dh1 dt. Okay, so now the instant in question is dh dt is given to be 0.5, right? Now, first we are going to look at the instant of 3 meters, okay? So what is given is that dh1, so dh1 is given to be negative 0.5 meters per minute. In the first instant, we are finding dv dt when h is equal to 3. So then we are going to do dv dt is 16 pi over 75, 3 times 3 squared is 9. So 3 times 9, dh dt is given to be negative 0.5. Okay, so then I have... So what do I have? 9 times 16, so 54, 4, 9, sorry, 144, 144 pi, negative 144 pi over 2 times 25. So that becomes negative 72 pi over 25 meters cubed per minute. So this is the rate at which the volume is decreasing from the conical tank. Now the rate at which the volume is decreasing from the conical tank, the volume of the cylindrical tank is increasing at the same rate because it is flowing from that tank to this tank. Now, what is the volume of a cylinder? Volume of a cylinder is nothing but pi r squared h. So here the radius is a constant. The radius is given to be 4 meters. So that means 16 pi h is the volume of the cylinder. So that means dv dt is nothing but 16 pi dh dt. Now we already know that the volume is 72 pi over 25. I'm dropping the negative here because the volume of the cylindrical tank is increasing. Okay. Now we are asked to find at which rate at which the water level is increasing here. So basically we are trying to find this, right? So we're trying to find this. So we have 16 pi dh2 dt, right? So dh2 dt, which is what we are asked to find, is nothing but 72 pi over 16 pi times 25. Okay, so this goes into 8, 9 times. This is 2 times. The pi and the pi gets cancelled. So we have 9 over 50 meters per minute is the rate at which the water level is increasing in the cylindrical tank when the height of the conical tank is 3 meters. Okay. We are going to do the same thing for the 1 meter. Same thing, we will just change the 1 meter to 3 meters and see what the answer is. I'll post the answer for you, but follow the same steps. Okay, so we saw a right triangle problem, right? Then we saw the cone and the cylinder problem. Now we are going to go back to seeing another right triangle here. Okay, so what it says is that the foot of the ladder is dragged away from the wall. So this is the wall. So it is dragged away from the wall at the rate of 0.5. So I'm going to call this distance x, this distance y. The ladder height does not change, so that 13 feet is a constant. So what is given to me is that dx dt is 0.5 feet per second. So you're dragging the ladder away from the wall. So x is increasing. So dx dt is positive. The question is asking you what is dy dt, meaning at what rate is the top of the ladder sliding when the foot of the ladder is 5 feet from the wall. So at what instant when x is equal to 5. Okay. So the relationship between x and y is that x squared plus y squared is 13 squared. Okay. So you take the derivative 2x dx dt plus 2y dy dt, and this is a constant, so the derivative is 0. So let's see what is given to us. We know that x at that instant that we want is 5, dx dt is 0.5, y at that instant we don't know, dy dt is what we are asked to find. So how do you find at that instant? So when x is equal to 5, this ladder distance is always 13, right? So we are going to use the same relationship. X squared plus y squared is 169. So 5 squared plus y squared is 169. Y squared is 169 minus 25, which is 144. So y is 12 at that instant. So then you finish this. So you have 5 plus 24 dy dt is 0. So that means 24 dy dt is negative 5. Dy dt is negative 5 over 24 feet per second. So as we are dragging this at half a feet per second away, this ladder is dropping at the rate of negative 5 over 24 feet per second from the top. All right, so we're going to finish it up with this problem. A balloon is rising, right, at 20 feet per second. At what rate is this angle of elevation changing when the balloon is 400 feet from the ground? So I'm going to call this y, and then I'm going to call this oh, so I just need y, that's it. So then I'm going to see the relationship between y and this 300 feet is fixed, right? So then the relationship between them is related by tan theta is opposite over adjacent. The question is asking you what is d theta dt when y is equal to 400. This is the question. And what is given to us is dy dt is 20 feet per second is given to us. So I take the derivative. The derivative of tangent is secant squared theta d theta dt is 1 over 300 dy dt. Okay. So now this instant that I have, this is my theta, this is 300. The instant in question, y is 400. Okay. So y is 400, and I at that instant this distance is 500 because it's a 3 4 5 right triangle. Okay, secant theta is reciprocal of cosine, so cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent, which is 500 over 300. So secant theta is 5/3, which means secant squared theta is 25 over 9. Okay, so this is at the instant in question. So then I substitute 25 over 9 d theta dt is 1 over 300 dy dt is 20. Okay, so then I do some rearranging to get d theta dt is 20 over 300 times 9 over 25. Okay, so this goes 3 times, this goes 100 times, 100 goes 5 times. So I get 3 over 125 radian per second is the rate at which the angle is changing.